For this example, we're going to solve a slightly different kind of transmission line and use that to solidify our understanding of the Thevenin circuit equivalent approach of solving initially charged transmission lines. So we start out with two transmission lines connected to each other. They're both 50 ohm transmission lines. And then at t equals 0 minus, they're all charged to 7.5 volts. And then at t equals 0, what we're going to do is we have this other 50 ohm resistor, and we are going to connect that onto this at t equals 0. And this is open circuit on both sides, so we charged it up and then disconnected everything, and then at t equals 0, we flip the switch. So the question is, what happens? So let's start out by going through, in this case, we're going to use the Thevenin circuit equivalent approach. So the first step, as I've listed, is you want to find the steady state voltage and the steady state current. So in equilibrium, if we look at this, there's basically 7.5 volts. And so the voltage at this junction, if we're just looking at this half here, is just going to be 7.5 volts, right? So it's not the most interesting situation here. VSS is going to be equal to 77.5 volts. And then ISS, before you hook this up, it's just all sitting there charged up, not hooked up to anything. So the current is going to be 0 because they're open circuits. And also, while we're on that note, since they're open circuits, we can also say that gamma 1 on this side is going to be equal to 1, and gamma 2 is going to be equal to 1 on this side, since they're open circuits. So the next step is we decompose. This is a step that's in common for both of them, is we want to decompose the VSS and the VSS into a positive going wave component and a negative going wave component. So you want to find VSS plus and VSS minus. And like last time, we do that by solving a system of two equations and two unknowns. First one is observing that the two of them added together is equal to VSS. And the second one is the difference between the two. And if we multiply the Z naught across to the other side is equal to ISS times Z naught, and since ISS is 0, it's going to be equal to 0. And so if we add the two together, we'll find that VSS is going to be equal to, 2VSS is going to be equal to, in this case, this is 7.5 volts. So adding them together, we'll find VSS is equal to 3.75 volts, VSS plus. If we add the two together, it's going to be equal to 3.5 volts and 75 volts. And then if we take the difference between the two, we'll find that VSS minus is also going to be equal to 3.75 volts. And so the next step, this is where we start doing the Thevenin circuit equivalent analysis, is to draw the Thevenin equivalent at t equals 0. So let's start drawing what this looks like, what this part looks like. So starting from this part of the transmission line, we have a voltage source that's going to be equal to 2 VSS plus, because that's the wave that's coming out. So 2 VSS plus. And then there's a source impedance of 50 ohm, this number here. And then that is going to get connected to this 50 ohm resistor here. I guess this part, I'll call this should be blue. Now we do the Thevenin equivalent for this part here, this portion here. So also 50 ohm source impedance, and then over here we would have another voltage source that's equal to 2 VSS minus, the VSS minus wave coming out here. And in both cases, they're both 7.5 volts. Right, so in this case, the voltage source here is also 7.5 volts. After that, the next step is to solve the circuit. for the voltage at the junction for t greater than 0, greater or equal to 0. So to solve this circuit, what we're going to do is if we identify the currents, there's 3 currents going on. Right? We have, we'll call this I1 going this way, and over here we have I2 going that way, and then we'll call this branch I3. So we have 3 unknowns, and we actually have 3 voltage loops, 3 Kirchhoff's voltage law loops that we can use to solve for these 3 unknowns, right? We have this left-hand loop, this right-hand loop, and then the overall loop. So let's start with this loop over here. So if we look at first equation we have is going to be 7.5 volts, and then 7.5 volts minus 50 times I1, and then minus 50 times I3 is going to be equal to 0. So that'll be our first equation. And then the next equation is, let's look at this left-hand loop here. We'll have 7.5 volts minus 50 I2 minus 50 I3 is also going to be 0. It's going to be equation 2. And then lastly, we'll look at this large loop. So we'll have 7.5 volts minus 50 I1. And then in this case, we're going against the arrow, so we have a plus 50 I2, and then minus this 75 volts, so minus 7.5, not 75. 7.5 volts is also going to be equal to 0. So here we are. This is the left loop, the right loop, and the overall large loop. So now we have 3 equations and 3 unknowns, and we just have to go about solving this. And oh, and also we actually have a 4th equation we can use, which is the fact that the current coming out, this I3, is going to be equal to I1 plus I2. So we also have I1 plus I2 is going to be equal to I3. So that's a 4th equation we can use as well. So this is actually a nice one. This is a nice pretty one to use. So let's just plug equation 3 into equation 4. Because if we rearrange equation 3, we see that I1 is equal to I2, since these 2 cancel out. And so we subtract this over, divide both sides by 50. So we see that I1 is equal to I2, which makes sense because the circuit is symmetric. And so we plug that in, we get I3 is equal to 2I1, and it is also equal to 2I2. So let's plug that into equation 1, and then we're going to get 7.5 minus 50I1 minus 100I1 is going to be equal to 0, and therefore I1 is going to be 0.05A, which is also going to be equal to I2, and then I3 is going to be double that, so I3 is going to be 0.1A. And so using that, we know that we can now find the voltage at the junction. So the voltage at the junction here, Vj, this is what we're going after, the voltage at the junction. Therefore, the voltage at the junction at t equal to 0 plus, and just clean that up a bit, t equals 0 plus is going to be equal to the I3 times 50, so 0.1 times 50, which is going to be equal to 5 volts. And so now, step 5, we want to find the new wave that's coming out is going to be equal to 5 volts, so Vj at t plus equals 0 plus minus what it was before. So what was the voltage here before? It was VSS, right? It was 7.5 volts. So 7.5 volts, which is going to be equal to negative 2.5 volts. And so we now know that the new wave that's launched, V new, is going to be equal to 7.5 volts. In this case, we also want to draw the bounce diagram. So let's go ahead and do that. So let's start by drawing it out and also listing our key parameters. So we have two chunks of transmission lines, and the reflection coefficient on each end is going to be equal to 1. We also need the reflection coefficient here, right? So the reflection coefficient here, let's just hammer that out really quickly. As the transmission line comes out, it's going to see the 50 ohm resistor that you put in if you're coming out this way, and it's also going to see the 50 ohm characteristic impedance of this transmission line. So it's going to have 50 and 50 in parallel. Basically, you can take the two in parallel, it's going to be 25 ohms. So the reflection coefficient at the junction is going to be new minus old, so 25 minus 50, over new plus old, 25 plus 50, which is going to give you minus a third. And since if you look at it from the other direction, you see the same thing, so the reflections off of in each of these directions is going to be equal to minus 1/3. And then in both cases, if you just wanted to look at how much actually goes out, the transmission crossing this boundary is going to be equal to 1 plus gamma j, which is going to be equal to 2/3. And so knowing that, we can now draw our bounce diagram. So before, what's our voltage? It starts out at 7.5 volts, right? So that's an important thing to keep in mind. And then at t equals 0, you have a new wave that launches in both of these directions. That's going to be minus 2.5 volts. And then it's going to reflect off of this open circuit. So that will also be minus 2.5 volts, because the reflection coefficient over on both sides is 1. So sorry, I'm looking at this, should be gamma 2. And then after that, this is going to reflect off of here as well. This portion is going to consist of the reflection off of here plus the transmission across this wave. So the two added together, you're going to find is going to be equal to minus 0.833. And then you're going to get the same value over here, minus 0.833. And then there's going to be a reflection of 1, so you get the same value over here, minus 0.833. So now let's find the voltages as you cross the lines. So as you cross this line, you lose 2.5 volts, so now you're only at 5 volts. And then you cross here, you lose another 2.5, so now you're at 2.5. And then here, you lose minus 0.833, so you get 1.667. And over here, you also have 1.667. And then over here, you subtract another minus 0.833, and so you are left with 0.833. So if you look at this circuit, everything was charged up, and then you basically run a resistor between the two rails. So you expect the whole thing to discharge down to 0. And that's kind of what you see here. So as these waves bounce back and forth, you see your elevation, so to speak, progressively decrease until the line discharges down to 0. And that's it. So as you can see, the process is similar to the other standard examples that we have. The main difference is when you're trying to solve the circuit. in which case you have to pull out your old circuit analysis skills and just find the best way to figure out what the voltage at the junction is for your Thevenin equivalent circuit that you drew. And once you find that, you just subtract it from what it used to be out, and then propagate the new wave.